this video, we are going to investigate how ANSYS solutions can help you model thick composite structures. This is the project page of ANSYS Workbench. The first thing we do is introduce a system for the composites analysis and define the materials we are going to use. We could do that manually or from an existing library of materials that you could have defined, or you could be using the one we provide. So here we are just choosing one material and putting it into our project. Then the next thing we do is define the geometry we are going to use. So in this case, we are going to take the file that corresponds to our pressure vessel, and we are also introducing a second system that will contain the non-composite parts. If we look at the composites model, we see that we start from a shell mesh, which is kind of the mold we would use, so the internal skin of the pressure vessel. And the second model has the two titanium caps that we are going to assemble with our composites model. Now we move on to the definition of the composites model itself. So we open the setup of the composite system, and here we are going to review the materials we are going to use. They have been automatically imported, as well as the fabrics we are going to use. So in this case, the fabric is basically a material with one thickness. We see also that we have defined groups of elements that will be used to define the plies, and now the next step is to define the zero orientation on the model. So we do that using a system of rosettes. So in this case, we are just going to use one aligned with the axis of our cylinder, and this one will be now used to create what we call an oriented element set. So basically, that's a group of elements on which we are going to define the orientation. So we take the element groups, we define the normal, could be one way or the other, all depends on how you want to set up the plies, and we use a given rosette. When we do that, we've basically defined the zero orientation that will be used for subsequent definitions. You see the yellow arrows defining this orientation. Now we can start defining groups, and we start with the first ply group, in which we are going to create our first ply. We again use the oriented element set to define where the ply will be applied, which material we are going to use, and what the angle is. So here we take as an example 20 degrees, and you are going to see through blue arrows the orientation of the actual ply when we pick it. So you see a 20 degrees orientation, but we may have chosen to change the angle to 45. So let's just change the number here, and we see that the plies will be automatically updated accordingly. In our case, however, this is a winded pressure vessel, so we need a slightly more complex definition of orientations, and for that we are going to use what we call a lookup table to define the orientations. The data in this table has been defined through an import of a table or through a Python script. In this case, this was a Python script, and will be used to define the ply orientation. So instead of defining a single angle, we are going to use the tabular data to define the angle. So that will provide correction angle, and this is based on the location on the model. So you could have something very complex varying with location on the model and so on. So you see here again the blue arrows defining the actual orientation of our model. Let's now move on defining other plies. So we can copy an existing ply, put it anywhere after, before, so you can manage the sequence of your plies. And we are going to choose for this second group another part of the table. And again, we update, we see a different orientation here on the model. So again, all the plies you will define can be defined using either direct angles or the tables as we've shown in the two previous examples. We can create now a new ply, and for this ply we are going to change slightly the location of the ply. So instead of taking the entire geometry of our pressure vessel, we are going to restrict to a portion of the model. So here we use what we call a rule, a parallel rule, that will define two planes between which the plies will be applied. So that could be also very useful when you put a reinforcement on your composite model. So you could choose just a local orientation, and even if the group does not exist prior to the definition of the composite, you can define them on the fly and use them on the fly. So here we see the ply has been applied only to those central and straight part of the cylinder with a 90-degree angle, which we clearly see here as perpendicular to the orientation we defined originally. And after that, we are going to define a few additional plies. At this stage, we can review through a section cut how the plies were laid up. So you see here the various plies, and you remember we had this reinforcement in the middle that gives us the drop-offs you've seen just before. And the next step is really basically to create the solid model. So we are using a couple geometric guides to make sure that we follow given geometry, and we are extruding all the plies to create a 3D model made of X elements and some wedges in the drop-offs that we are going to reuse when we assemble them with the caps that we have defined in this second model on our project page. And here you can review each and every ply within the 3D model, obviously, as you could do on the shell model. So now we have all of our models, both the composites and the non-composite parts, that we are going to assemble to create a static structural analysis of it. So basically we create a static analysis, take the setup from the composites definition, take the setup from the non-composites parts, and we are going to update the system so as to assemble both parts together. Once the model has been updated, we can now look into the static analysis, and as we will see, we have here both the composites part, the middle pressure vessel, and the caps all together. So we can take a look at the mesh of each part. We can hide one cap and look at the mesh of the composite. So you see this is exactly the model we had in our composite system. And connections have been created in the form of contacts. So we have contact between the caps and the pressure vessel, and we are also going to define a number of boundary conditions, especially the pressure within the vessel. The only thing we need to do then is to solve the model and look at the results. We could look at the standard results like deformation and stresses, but let's concentrate here on the failure of the composites. So here is our composites model again, and we have just removed the caps to work only on the composites part. So what we see here is a ply-wise result, so we can look at each and every ply and look at a scalar value called inverse reserve factor that tells us where the critical areas are. When it's above 1, that's a danger area that may fail, but at this stage we don't know which ply or for which reason this is going to fail. So that could be the next step here, when we are going to take a look at still the same factor, but also look at the critical layer. So we want to get not only the global information, but also the local information as to which ply has failed and for which reason. So this is what we are going to see next when the graph is updated. So we can look here, and we can display on all elements using this small A button here, a text on each element that tells us which ply, which failure criteria, and also possibly which load in the case of a load combination or load case combination. We can also look at one given element through the entire thickness, so through all plies at a given location. And here we can choose to use the analysis plies, show the thicknesses, show the failure criteria, show the strengths, or show the stresses. So this is very configurable graph that we are going to create here. And once the graph has been created, so all results are computed on the fly here, we get a view of the ply, so the sampling elements, and the y-axis represents the ply we are looking at, and the right-hand graph shows the evolution of the failure criteria, for example. It could be again stresses or whatever. The last thing we are going to look at is how to change the model. Let's say we want to put more plies because we have identified there is a potential failure. So we want to take a given ply group and increase the number of plies that corresponds to this existing group. So here we change the number of layers from 1 to 4. We are going also to change our central part. You remember the one we had localized, and add 4 layers as well here. And ultimately, we just need to update our model. And the last thing we need to do, that's all we need to do before we recompute the entire model and can look again at the results. So here you see we've increased the number of plies. And the last thing we would do is update the project and look again at our results. If you want to learn more about our solutions, I would suggest that you contact the local offices near to you by visiting this link.